I think one thing I should add to the introduction is that the way you get interested in philosophy and history of science is that you're doing your PhD and you sort of start asking the usual PhD student question, which is, what is it that I'm actually doing here? And if you sort of just do it in a pub, then it doesn't turn into another interest. But if you do it in a sober state, then you might actually start wondering, like, how does science work, and why we do things in the ways that we use. And I think this talk is trying to use the same sort of way of thinking, or some of the methods that philosophers of science use when trying to understand how science works. And I'll try to use some of these sort of ideas to talk about errors in programming. And I think it's an amazing, sort of fascinating history. So there will be a little bit of historical aspect to it, a little bit of like, why do we think about errors the way we think about errors? There's a lot of different takes on errors. So you could ask, like, how important errors actually are. Are errors in software something that is like threatening the whole industry and will turn into crisis and everything will stop working, or is it actually just fine? And if you look back, Charles Babbage in 1837 wrote, "If trials of 3 or 4 simple cases have been made and are found to agree with the results given by the engine, it's scarcely possible that there can be any error." So you just write your program for the analytical engine, run it 3 times, gives the right results, you're fine, it will work. That's what he used to think. And even in the sort of very early days of the ENIAC machine, the sort of narrative about errors was that the ENIAC woman would simply set up the machine to perform these plans, and this is just a trivial mechanical problem, and that this turns out to be difficult and actually require a lot of thinking. That was something that the sort of people in the industry completely didn't expect. So they said, well, we'll have these programmers who will write the plan or design the mathematical plan of the computation, and then we'll hand it to the ENIAC woman who will just do the clerical coding work. And it turned out that this is actually the hard part of it. And it took people a really long time to realize that programming is really hard problem and there's lots of errors. And by the end of 60s, people were actually mostly talking about crisis. And ever since the 60s, when people realized that it's actually hard, managers, academics, and governments would release warning about the desperate state of the software industry. So I think that the fascinating lesson here is that we went from Babbage saying this is trivial to this kind of a newspaper article that says the doomsday will happen on January 1st because of the Y2K error. So it's really, I think that this sort of overall part of the history is really just fascinating, how the perception of how important errors are changed completely. I'll be citing a couple of books. I'll give you references at the end, but this one makes a really interesting observation that we live in this perpetual crisis of software engineering, and yet this is one of the sort of most profitable and successful industries of all time. So, like, how does this fit together? And I think the sort of interesting story is that programmers in different programming communities or in different parts of the industry somehow learned to deal with errors. And we've sort of developed lots of different practical strategies for dealing with it, and I'll try to just quickly talk about 4 of them. And they're sort of represented by these personas. And the first part is that you just see error as a natural part of the programming progress. They sort of happen. You can't really avoid them. And you should try to do something to avoid as many errors as possible. I think this is one of the sort of earlier attempts that keeps happening in the more sort of software engineering-oriented part of the industry, where in the early days when COBOL appeared, the aim was COBOL will eliminate the need for skilled programmers. And that didn't happen. The other fun thing about COBOL is that it was designed by the so-called short-term committee, which was trying to build something that will be good for a year or two. And it ended up being used for 50 years. And when people sort of, sorry? I can't count, but it will be used for hundreds more years, definitely. But people sort of realized that maybe the industry realized maybe this is just a management problem. Like really, we just need proper management, and that will solve the problem. And there was an event organized by NATO, a conference on software engineering in 1968, where the main message was that this black art of programming has to make way for the science of software engineering. And that typically meant software engineering as proper management of these sort of weird programming people who are difficult to manage. So it was sort of mostly seen as we just need to turn it into a proper engineering business, and then it will work. And that sort of continued since '68 for a long, long time. And I think it's really interesting when you sort of see the history and link it with what people are saying about software development in more recent years, where with the software craftsmanship movement, we again sort of emphasize the individualities of the software developers, and we say, well, you really shouldn't be focusing on these processes and tools and the sort of managerial software engineering methods, but we should go focus again on what in the NATO times they called the black art of programming. So I think there's a sort of interesting history there, and I'm going to be talking more about the way errors are dealt with in software craftsmanship or in test-driven development, because I think this is really an interesting case where we practically deal with errors and we use them in some way. So I'm sure many people here are familiar with TDD, and this is just a quote that sort of defines it, where we say we will only write new code if automated test fails. So that's the first point. And I think this is really interesting because it says it uses error to build software. Like, we're not saying errors shouldn't happen. We say, well, we first need to produce the right error, and we introduce the error, find the error, and then we write the code to eliminate it, and the sort of test becomes a part that sort of traces the error in the software, but the error becomes sort of something that we actually use to sort of build the software, and it becomes a part of the specification that explains what is it that the software is actually doing, and it serves also as a documentation. So we've gone from a world where we sort of say, well, we'll just properly manage people and errors will sort of not happen, to a place where we use the errors in a very active way as part of the development process to build correct software. And that was one take on error, and there's another take coming from the sort of more academic or more logically sort of grounded community. And in the very early, in like 60s, there was an article in the ACM, which is the sort of academic programming community, saying, well, we, the ACM members, have read many non-ACM or industry articles on data processing, and they all suffer from one basic fault. They fail to report any fundamental research. So I think the perception was that the data processing problem is just trivial and there's nothing interesting there. And instead, the approach that sort of appeared in the academic world was, I think, very nicely captured by the ALGOL programming language, which was labeled as remarkable computer science achievement. And it was an object of beauty, which was never widely adopted. And many of the things that happen in sort of academic research still come from this idea that you should formally define your languages. So this sort of become a defining an object or something that influenced the community and defined what the problems that we can ask are. And ALGOL really sort of started with this idea that you should have formal specification of what the language does, which people didn't do before. And Mark Priestley, who's doing a talk in the next slot, I believe, has a nice book called Science of Operations, and he sort of identifies the common idea in the ALGOL research program, where the goal was you utilize the resources of logic to increase the confidence in the correctness of the program. So you don't do debugging, you just construct a correct program. And that's what you could have seen in the keynote. That was a nice example of construction of a correct program. But of course, the difficulty is you have to sort of know what the correct program is. This is something that sort of, you can trace it to the modern days programming languages research. So exactly the same thing that they were saying about the ALGOL research program, you can sort of hear now when people talk about dependently typed programming, where this is a quote from a recent book trying to sort of explain it in a practical way, where the author says, well, you would think that the cost of formal program verification is too high, but we can now finally, 50 years later, show you that program verification can finally work. And I think there's another sort of related thing that I'll mention later, because we're sort of shifting from the program code to the properties, to the formal sort of specification. But I think this is, again, a nice sort of trace through the history where you can see something that appeared very early in 50s and 60s and sort of traces through the academic programming languages research to the things that we are doing as cutting-edge research today. And I think it's a fascinating story that sort of 50 years later, we're still saying we will finally figure out how to make the proofs thing work. And when you sort of see how the idea appears in the universities, this is logically the thing that we must be doing. Because in the sort of early days of computer science, finding like a formal mathematical program or agenda, that's what made computer science possible as an academic discipline. And you don't have like science of telegraph or science of trains or science of cars, because there was no sort of formally or any like a well-defined program for what is the problem that we are solving. And I think with sort of computer science, having algorithms and trying to prove things correct gives us a really nice sort of goal that is academically credible. Mathematics is a perfect part of the university environment. So I think it's very sort of natural to see this progression. And you can sort of see how it somehow interacts, somehow doesn't interact with the data processing people who are solving all these trivial problems, like writing all the banking systems and stuff. In many areas, using program verification actually works really nicely these days, but in some areas, it doesn't seem all that useful. And I'll get back to that topic in the conclusions and try to sort of figure out why that might be the case. The other amazing thing, so this is, I think, 1993, Sir Tony Hoare, who's one of the founding fathers of the sort of formally trustworthy programming research, wrote this paper where he's sort of saying, well, all these industry people, they're not doing it right, but how is it possible that the software they do sort of works? And in the introduction, he's sort of quoting how many people died because of software errors, and it's not much. It's like, well, depends on, if you could say compared to zero, anything is too much, but if you say compared to the car industry, I think the number is something around sort of 10. So it sort of mostly works, but it's not using the right things. So how is that possible? And I think that the first approach that I was mentioning, just doing proper software engineering, and as that might be changing over time, is actually often good enough. That was my first persona. This is my second persona, and I'll have two more personas that also learned to deal with errors in a way that mostly works for them. So the other approach, and I think this might resonate with this conference, is just saying, well, errors will inevitably happen. We can't get rid of them. But, and that's of course what the Erlang language uses and how the community thinks about errors, where if you look at long-running distributed systems that run on lots of small, cheap devices, errors will just happen because even the probability of the cosmic ray flipping a bit is actually pretty high. So this is sort of a completely different approach where, again, you sort of accept that errors somehow happen, but we deal with them in a different way. And I did read Joe Armstrong's thesis where he says, he distinguishes between these two different concepts. One of them is an exception, which happens when the runtime system doesn't know what to do. And the other is an error, which happens when the programmer doesn't know what to do. So errors are expected because the specification is not complete, and when you receive a message that has wrong bits in it, you just don't know as a programmer how to react to it. And this is amazingly very different kinds of errors than the ones that we, for example, handle with tests. And what do you do with errors? Well, in Erlang, if you if you get into the errorless situation, you just let someone else deal with it, and what you have to do is you let the process crash. Or I think as Joe's thesis says, you just kill yourself. And this is, again, sort of an amazing approach, because you just say, well, errors will happen, and when they happen, we'll have to somehow deal with it. and the only thing we can do is shut down this particular process, but because of the structure of the runtime, you'll have other supervising processes that will take care of restarting the system and recovering from that error. And if you think of it, like this is exactly the opposite approach to errors than what people with writing tests might want to do. Because if you're writing tests, you're basically using the error to specify how the program should behave. You're saying, like, this is the specification for what it does. And errors in Erlang are errors that happen exactly when you don't know what it should be doing, when you don't have the specification. So there's sort of two communities here that both use errors in some way or deal with errors in some way, but the notion of what the error is completely different. There's interesting question, and I don't know the answer, but if you're sort of in a system where you expect errors, should you still call it an error? And I think it makes sense to call it an error because it's a good name for the thing that happens. But if you approach this same problem from the sort of maybe from the academic perspective and you try to prove things about Erlang, well, if it's handled in a sort of expected way, then it's not really contradicting my proof. It's just part of how the system behaves. So that's another take on errors, and I somehow all my errors, all my personas are manifested in this conference, which is beautiful. So this Lego figure doesn't quite look like Sam Aaron, but Sam is playing tonight, and in the live coding or live programming community, errors are dealt with in yet another really interesting way. So, and it sort of historical fun remark is when in the early days, all the businesses tried to hire lots of programmers and nobody quite knew what a programmer is. They went through sort of trying to figure out what are the personality traits that programmers have. And I guess as it often happens, they sort of didn't really find anything distinctive. But there was one sort of study, reasonably credible, that was saying, well, programmers are just like any other people working in the industry, but maybe they are slightly more musically talented or like playing chess. So there was this sort of early days idea that if you want to hire a programmer, you can hire someone who's good at maths and solving puzzles, or you could hire someone who's a good musician, or you could just hire someone who's good at dealing with machines in general. But the musician sort of trait was partly there as well. And I think one of the sort of early systems that took very different approach to programming than the other ones that I was mentioning was in the Smalltalk language, where the way the language works, and this is something that you don't really sort of see today, because when you hear about Smalltalk, they'll tell you, well, this was the first object-oriented programming language, and you think about, well, I think people here probably don't think about Java, but many people will think about Java, and you'll imagine all these classes and lots of code. But the thing that was really different about Smalltalk was that you didn't think about programs as a linguistic entity, there's like massive pages of code. But it was thinking about programming more as an interaction. So programming is interacting with the system, with the running program. And if you write some Smalltalk, you start your Smalltalk VM, and that's your Smalltalk program running. and you modify it and you sort of interact with the program live, which is something that's very different from this idea that we have some program code that we analyze and look at, and when we are happy with it, we run it and ship it to production. And so this focus on interaction, I think, is what sort of you can again trace to the modern times with things like live-coded music, which you'll see tonight. And there's a couple of people who sort of write interesting things about this way of thinking about programming. And one of the really interesting points is that if you relate it to music, in musical genres where they're not closely or precisely notated, there are really no wrong notes. There are only notes that are more or less appropriate for the performance. And with live coding, this is what you're basically taking into the programming system. So live coders may prefer to accept the results of imperfect execution or an error. And when you get an error in your live coding performance, so watch Sam tonight very carefully, what the people might do is that they'll perhaps compensate by manual intervention, by playing something different that fits well based on the sound you heard when the error happened. And maybe it will actually turn out to be more interesting. So when you accidentally play an error in a live coding performance, what might happen is that you'll actually play something better than what you were planning. And so here, the error is really more of an inspiration or something that you sort of lets you be more creative. And that's sort of specifically in the live-coded music or live-coded music area. But I think there are very many interesting lessons that you can learn from this approach, even for sort of proper software engineering. And one of the really key things here is that what makes this work in live coding is that you get to see or hear the error immediately. So you hear that something is behaving in a different way and you react to it. And so the two really important things here are you make the error visible or hearable, and you build the tool so that you can quickly react. And every time I read something about DevOps or read something about how people have pagers that will ring them when something on a website is wrong, and then they have to open their laptop and fix it immediately, I think they're doing live coding with very crappy tools. So I think there's a lot you can learn here. And I've got a couple of, so I went through these four different approaches that I think different communities in the industry use. I don't think they're quite perfect categorization. So if you think there's some more, definitely come and talk to me later. But I think the sort of thinking about errors gives you a really nice way to structure or have some sort of structured look at how the industry works. And the other part that's interesting about errors is that often it's actually really hard to sort of classify what is an error and what kind of error is it, which is one topic I didn't really talk about that much. But if you look at a recent famous error, so this is a Google Translate around the time of the Ukrainian crisis or the Russian invasion to Ukraine. Google Translate started translating, if you took words in Russian and translated them to Ukrainian, it would translate Russia as Mordor, and Lavrov, who's the foreign minister, as sad little horse. And of course, this happened because Ukrainians writing on the internet referred to Russia as Mordor, and Google Translate learned this. So it's operating perfectly according to the algorithm, but it's probably not what the authors expected. So what is an error? I think when you sort of think about it in the very formal sense, this was perfectly correct, and if you had a proof that Google Translate works, it worked. But it did something that we didn't want to. And this was the less bad of the two examples I came across recently. The other one was Google Photos or Google Pictures, I think, recognizing or putting black people in the category with apes, which was really, really bad. And you can see how the algorithm sort of leads to this, but it's ignoring the society aspect of it, where we just, even though like we wrote the algorithm and it works according to the specification, it doesn't do what we want it to do. So I have two more errors for you, and I think those are interesting. So one interesting error, and these are from some perspective less sad than the previous one. So there was a trading firm called Knight Capital, and they've lost, how much is this? $400 million, because what they did is that they had software and had some sort of flag somewhere, and they repurposed the meaning of the flag to mean different thing and deployed a new version where if the flag was on, it would do something clever. And then they deployed the software on all servers except for one, which was running an old version where the flag meant something completely different, and as a result, it started selling all their whatever they do, I don't know, for cheap. And I think this is a really nice case study because you can look at it through the 4 different perspectives. So if you're a live coder, then you'll say, well, it really did took them 45 minutes just to shut down the server. And it did because they just didn't know how to they didn't have the right access to the system to figure out what's the server that's misbehaving. They didn't see or hear the error, and they couldn't sort of intervene quickly. So maybe if it took them like a minute, they would just lose 10 million, and that's fine. The Erlang answer is, well, obviously that server should have killed itself because it received a message that was incorrect, and that's what you do. And then you can say, well, this whole thing is a madness. You should prove that your system is correct, and this cannot possibly happen because your proof will tell you this change where you're changing the flag will violate some constraints that you have on your trading strategies, and it will give you a nice, short, clean error message that's easy to read, telling you this is where your proof fails. And I think the related interesting question here is, well, what is it that we actually need to test? And what are the cases that we haven't covered? Or more interestingly, if you're using something like Quick Check, what's the property? And it turns out that the last two are actually very similar. So whenever you hear people saying that there's like a massive opposition between the tests and the types with proofs, they're very often talking about the same thing, because you always need to know what's the property. So what is it that we could have said? Well, we could have said maybe if you're trading, then you're only allowed to change some price of something by this much, and then either prove it or write a test using something like Quick Check that covers that. So what I think is really, really interesting here is that when you look at any software-related error in the industry, you can see these different ways of thinking. So I think one thing that I would like you to take away from the talk is that you can think about the problem in very different ways, and you'll often end up with different answers that all make some sense in some context. My other popular error, so this is the end of the world, which was supposed to happen at the beginning of the year 2000, and it didn't happen. So there was lots of money spent on preventing the Y2K error, and again, you can sort of try to prove or test some properties. And this one is really interesting because because it partly relied on a very low-level representational error. So if you have a proof on a paper that says, I'm doing my dates correctly, you will usually just say, well, year is a number. And the fact that it ends up being represented as 2 digits would very often be just a technical detail. So you'd have to be very, very careful to actually sort of, once you realize that the 2-digit representation is a problem, then you don't have to finish the proof. You can just go and fix your integer representation. I think it does give you sort of very nice way of thinking about it and finding the error. And the other interesting thing about Y2K is that what happened in the end is that companies spent a lot of money trying to fix it, and then they just had someone sitting there by the computer around midnight waiting for the system to crash and sort of saying, well, let's see what happens and if I can then get it back to run. And again, this is the live coder there sitting with very crappy tools waiting for the doomsday and thinking, well, do I actually have enough tools to fix it when it happens? So to wrap up, there's the one thing I mentioned in the beginning, which is that software industry, even though it's the most sort of fastest growing of the fastest growing sectors of the US economy, we somehow live in a world where we are in a constant crisis. And it's really interesting to sort of think about this and try to figure out, is it that we are actually not doing right, or is it that maybe we are just don't thinking about it in the right way? I think there's lots of things you can learn here. One is that if you have some nice basic assumptions, then, well, the big picture is there are very often different ways of dealing with a problem. So if you have some basic assumptions that you can prove or test, then that's perfect, and you're very lucky, and do that. But if you have some system where you really don't quite know what the exact sort of specification is, or what is it that it should be doing, then taking some idea from the other approaches might be very well the thing that you need to do. And I often think that the problem isn't like, is it ethical to write programs without proofs, or is it not ethical? The problem is, what's the sort of easiest way to describe what the program is doing? If it's easier to write code and read the code and say, yes, this does what I think it should be doing, then you should write code. But if it's easier to write a formal property that describes how it should be done using types or using dependent types or using quick check, then you should write the property, and maybe in the bright future of Agda, it will just fill the rest of the code for you. But if you don't know what the property is, then that's not really going to help you. And the last bit, I think the live coding experience is interesting because it sort of finds different ways of giving you this quick response. So if you have to have a human there, which often you do, you can learn from what Sam will be showing tonight and figure out how do we actually enable the people to react appropriately and quickly. So the 2 points are, there's lots of different ways of thinking, and often when you sort of hear people say something about errors, you have to understand what is the context in which they're saying it. And the other is, I think it's interesting to think about, is it actually easier to write the code, or is it easier to say what the code should be doing in some other way? And that's the end of the talk, and I'll just wrap up with these 2 books that are interesting and amazing resources that I've used a lot and enjoyed a lot. Thanks. And I believe we do have some time for questions.
What if there are no errors at all?
Well, Charles Babbage lived in that world, but I don't think that's happened since the analytical engine. Yeah, it would be nice if there were no errors, wouldn't it? Oh. Yeah, so the question was, what if we are just not seeing them? Yeah, I think this is the sort of interesting question about what is an error. If my plane lands, then I'm okay with not seeing the error. I like the idea of having lots of errors that you don't see. I guess that's what sort of partly happens in the Erlang style, where if you have an error, you just recover from it, and you're using it more as a sort of mechanism within the system. So that's one way of having errors that you don't really see. I guess you might still see them in a sort of performance log when you realize that some process is running really slowly because it needs to restart itself after sort of every other message. But yeah, I think that's a sort of topic for another talk about what is actually an error. We've got one more question over there.
Thanks.
So in a world where one man or one woman's error is someone else's exception, how should library authors approach the problem of catering to both audiences?
Yeah. Well, I think so with the different examples that I was using, they don't often sort of end up being used together in the same system. So if you're writing system in Erlang, then the errors sort of happening within that will be isolated. And if you're doing live coding, you won't suddenly sort of plug in some things that you won't have a middle of your program that you'll want to prove correct. Or at least that's something that nobody has quite done yet, and maybe we should. I think there's another sort of interesting option, which is that you could have multiple different layers of things. So if I have an airplane, I maybe do want someone like Connor to write the low-level bits of the airplane, and with proper proofs that it will not like flip itself, or it will not, I don't know what else airplanes do. It will not sort of speed one of the motors to the max and the other to the min. But then that's a very sort of small layer that just covers the basic properties or basic assumptions that are easy to say. And then I'm perfectly happy if the pilot can do live coding on their airplane to sort of find the way they think is the best, because that's something we can't formally describe. So you could have multiple layers where at some very basic level you can prove some basic assumptions, and that's sort of eliminating one kind of errors from one part, and then use another layer where you deal with errors in a different way. But I think sort of crossing the boundary in all possible ways, that's still a tricky thing.
So I write Erlang, and as you say, there's lots of errors that sort of don't matter and are handled. But there's also some errors that really do matter, and then everything crashes and everything's horrible. So I wondered if you just thought practically about how to distinguish those two, because in my experience, treating all errors and like let it crash all the time results in like horrible things where I get woken up in the middle of the night.
Yeah. Well, I think there's a lot more Erlang experts in the room who will be much better at answering the question than I am. And I sort of did try to, there's definitely two kinds of errors in Erlang, where some of them are the sort of recoverable errors, and some of them, if you just write code that crashes all the time, restarting it won't help. So yeah, maybe you sort of need to talk to the live coding people and make the really bad errors produce really ugly sound. And I don't really have a good answer to that. I think this, maybe that's a place where sort of looking at the different communities and seeing what we can steal from them could be a way to go.